Okay, so, Scott Wynn, are you here? All right, well, Scott is, someone's mentioned this morning that we generally put on a pretty good program in this conference, and the secret to that is the contributions of AFCEA's Technology Committee as well as GMU, of course. And so Scott is one of our number of contributing committee members, and he has worked to assemble the session you're about to hear.
Thank you. Good afternoon. I'm going to make this real quick. It's an introduction. It's my privilege to introduce the following two speakers. I'm just going to read so you get the full background. Dr. Don Miner specializes in large-scale data analysis, enterprise architecture, and applying machine learning to real-world problems. He's the author of the O'Reilly book, MapReduce Design Patterns, as well as other O'Reilly reports around Python and Hadoop. He's applied machine learning techniques to analyze data across several verticals, including financial, retail, telecom, healthcare, government, intelligence, and entertainment. Our other speaker, Karl MacMillan, is a creative software developer with deep experience in computer security, OS design and implementation, image processing and recognition, audio processing, and numerous contributions to open source. Software that Karl created ships as part of several commercial products, open source projects, as well as the Linux kernel itself. In addition to writing software, he's published numerous papers and co-authored a book, SE Linux by Example. If you're familiar, it is the definitive work on SE Linux. So it's my privilege to introduce to you Dr. Don Miner and Karl MacMillan. Thank you.
Good afternoon, everyone. I'm really glad to be here. I'm really glad to talk about this. We hear a lot about machine learning these days. We heard a lot about artificial intelligence. I think in a lot of ways it lives up to the hype. What's happening now is really interesting, really amazing. We can do a lot with that. But we're going to just now start to hit a lot of the problems that are going to come as people attack these systems, as malicious actors try to subvert what we're trying to do with machine learning. And it's time that we start to face that. Those of us that are trying to apply this, trying to use this, especially use this for mission-critical applications, we really need to get our heads around what does it look like when someone tries to subvert a machine learning system. So a lot of this can be avoided by thinking about these systems in the right way. When you read the news, when you look at what's out there, it's tempting to think about these things as a replacement for human intelligence or something that's imitating human intelligence, that what's going to come out of these systems is going to look like a human brain and react like a human brain. And I think in a lot of ways that's not what's going to happen, at least in the foreseeable future. The systems that are being built today learn from examples. They can do tasks that humans can do, but they do them differently. They do them without the sort of intelligence and insight and context that human intelligence uses. And instead, these are systems that are focused and are capable of doing specific tasks very well. And in a lot of cases, that specificity, that focus that these systems bring help them outperform humans. So there's good to this, but it means in a broader sense that when they fail in ways that a human wouldn't fail. And I think if there's one thing that you can take away from what I'm saying today, it's to keep that in mind, that these systems fail in ways that are not like a human failure. And as we build systems and we rely on these systems, we need to understand what those differences are. We need to understand how they might fail, because that's going to help us protect ourselves from malicious actors. So let me give you an example. This is a picture of a planetarium. And a researcher was able to take this picture and change a single pixel and make a machine learning algorithm think that this is a mosque instead of a planetarium. So, okay, this is sort of a wacky planetarium. You could see how it's confused in some ways, but if you look, the magnified portion of this is that single pixel. It's a pixel up in the sky, right? And no human's going to take a look at this picture without that pixel changed, and then with the pixel change, and change whether they think this is a mosque or a planetarium, right? This is an example of how a malicious actor can take input into a machine learning algorithm, change it slightly and get a drastically different output from it. This isn't an isolated example. These same researchers did a huge number of examples, and these examples are interesting because not only are we changing things greatly, making the system think a horse looks like a dog or a bird looks like a frog, these are robust across different machine learning systems. So they're able to change, again, a single pixel and confuse multiple systems. Okay? And this should be terrifying in a lot of ways, that they fail in these ways, these sort of spectacular ways with minute changes. And what I want to do today is I want to sort of go through how these systems work at a high level, and I want to then help you hopefully get an intuitive understanding of why systems might fail in this way, right, and why they are vulnerable. So one thing, to think about is instead of this beautiful, intelligent robot, there's more Homer Simpson here, right? So the key thing about Homer Simpson is his focus on beer and donuts, right? And these systems have that sort of minute focus. And a leading researcher that received the very prestigious Turing Award for his work in the foundations of machine learning recently said all the impressive achievements of deep learning amount to just curve fitting. So I'm going to tell you what curve fitting is in a second, but what he's really saying is that these systems aren't intelligent. They don't know what horses and frogs and planetariums and mosques are in the way we do. They don't have an understanding of what they are. What they're really doing is they're noticing patterns. And they're noticing that this picture that you're showing me is similar in a certain way to other pictures of planetariums or mosques. And the way that it looks at that similarity is key to how that it succeeds and key to how it fails and how it can be attacked. So in order to sort of give you this understanding, I want to address the most important technological gap that's preventing us from having automated bartenders, which is what's the difference between a lemon and a lime, and how can we teach computers to understand them? So at the heart of machine learning, what we're going to do is we're going to take examples, and we want to show these examples to the computer, and over time, it's going to learn to recognize new things based on the examples that it's seen. So it always has to start from just, you can't show it an actual lemon or lime, you're showing it a picture of it, and it's going to notice certain things. And so in this example, the computer's been taught to recognize color and size. And the notion is that lemons are slightly larger in yellow, and limes are slightly smaller in green. And so if we take examples, this is the training data, and we mark them on this chart based on size and color, what happens is that you can show the computer a new example, and we can hopefully figure out, is that new example or a lemon or a lime? So what does this look like? How does the computer actually do this? Well, if you'll notice here, these fell into two groups, right? We have the slightly smaller green examples, which are the limes, and the slightly larger yellow examples, which are the lemons, and you can draw a curve between these two groups of things. And once you've drawn that curve, when you see a new example, all you do is say, which side of the curve is it on? Is it on the lime side of the curve, or is it on the lemon side of the curve, right? And in this example, we've shown a lemon. And this is what essentially was meant by deep learning as just curve fitting. We're just dividing these groups with curves, and we're trying to figure out whether the new things are on one side or the other. Now, in the real world, of course, for real machine learning systems, we're noticing a lot more than just size and color. We'll notice hundreds or thousands of things. And this noticing different aspects of the data coming in is called feature extraction, right? So this is where we take the incoming data, we notice interesting properties of it that would help us make decisions, right? And we extract those features. And then we use those features to build a model. And so what this is showing, essentially, is that that way we draw the curve or draw the line is hugely important. These are several lines in this example that separate these data. Some of them are good, some of them are bad, one of them is the best. Okay, so these two aspects of machine learning are really what determines how well it works. How well can we notice things that are interesting about the data coming in, and then how well can we then group those things together so that when we see new examples, we can figure out which one it is. So the problem with all of this is that feature extraction stage. So when I started doing this, when I started first doing machine learning, you would do feature extraction by hand. You would write software that would notice things. And if you're doing optical character recognition, you would notice things about the shape or the size or the number of openings in the characters, right? And you would handwrite code that would recognize those things. And it was hard because sometimes you wanted it to show the same feature regardless of the size of the letter or what font it was in. And sometimes you wanted it to be invariant to rotation, like I don't care whether the character's rotated, or sometimes you do want it to be rotated. And what's really bad about this hand feature extraction is once I've done all that hard work for creating a set of features that work for character recognition, when I want to use an algorithm to recognize lemons versus limes, I write a whole other set of very difficult code. And when I want to recognize the difference between horses and dogs, it's yet another set of code. And it was really that was the limitation for a lot of machine learning, that those features were enormously difficult to code and to research and to understand. So that's, in a lot of ways, deep learning, the most interesting and exciting part of deep learning is it gets rid of that. So most of the time when people talk about deep learning, what they're talking about is a neural net that has a bunch of layers, and the extra layers is what makes it deep. That's where the deep comes from. But what's really driving this is that most of the time when we're talking about these kinds of pattern recognition systems, it's something called a convolutional neural net. And the magic in the convolution is that we give the computer these tools, these sort of variable tools to do feature extraction. So you can think of the convolution that it does is the very basic building blocks of the kind of feature extraction I was talking about, and that the computer can control that with a couple of parameters. And so you build these layers in these deep learning systems of convolution. So it'll have a layer where it does convolution, a layer where it groups the results from that are interesting together, and then another layer that does convolution. So in this way, it's able to not only learn how to group things, it's also able to learn how to extract the features. So instead of having to write code to extract the features, you actually let these neural nets learn how to extract the features on their own. And this is hugely beneficial. It means that we can take a deep learning model and we can use it to recognize characters or objects or anything that we want simply by showing it enough data and training it over time. And what's really made this possible is sort of two things. It takes a lot of data for it to learn how to extract features and to learn how to do this compared to the old machine learning systems. And it takes a lot of computation. And so the computers being faster is really what enables us to do this. So the next thing I sort of want to show you, though, is the features. This is a visualization of what the features look like that it's extracting. So before, I was talking about size and color and things that would make sense to a human to notice about these objects in order to determine the difference between them. And a convolutional neural net, it's noticing something a little more abstract. It's noticing something that makes sense to the computer, and that if you're trained in this, you can sort of understand what it's doing, but it's not at that same intuitive level. And so the end result of all of this is that it's a little harder to understand what the neural net's doing, but more importantly, again, it's paying attention to sort of minute details that come in and building those up over time into something that it can use to make a decision between these two things. Okay. Fair enough. So let me talk then about sort of the result of doing it this way. So deep learning is amazing. It's done amazing things. But at the end of the day, it causes some problems. So part of how I got here, so I did machine learning at the beginning of my career. I did computer security for a very long time. And then more recently, I built a consumer app. And the consumer app was trying to use machine learning to try to look at teens' social media feeds and figure out if they're doing things that are bad or bad things are being done to them. And so one of the things that people, of course, care about is what are the pictures that their kids are sending, and is there nudity involved, right? But my problem is that when you combine Instagram and the beach and 13-year-old girls, you get pictures of bathing suits, okay? And at the beginning of this, I was using a service from Google. If you've ever used Google image search, they have something called Safe Search, and you basically say, hey, please don't show me images that have nudity in them, right? So that seems on the surface exactly what I needed to be able to do this, but I was doing the opposite. So from Google's point of view, you're saying, please hide all the images with nudity. So that means if they inadvertently say an image has nudity in it and it doesn't, that's all good from their point of view. You know, yeah, you didn't get that one result back, but the reverse is much worse. If you don't say that an image has nudity and it does, and they show that to you, that's a much worse outcome. I had the reverse problem. I was looking for pictures of bad things, and so that if I had these false positives, if I said something had nudity in it and it didn't, and showed it to the parent, they thought, okay, well, this app sucks and I don't know what it's doing, right? So what I had to do was you had to build, with the help of some of Don's people, we built a system that was tailored to our specific problem. So basically what we did is we got a lot of pictures of people in bathing suits and a lot of pictures of people in lingerie and nude pictures. And there's fascinating stories about what that process looks like in a workplace. But we basically showed the computer all of these images, okay? And then once we were getting some reasonable results out of this, we started to test it on some more real-world data. Now, some of you may actually already be seeing the problem that we ran into, but let me give you another hint here. The hint here is that, well, sometimes people wear bathing suits indoors, and if you look at bathing suits and lingerie, sometimes the appearance is not really the difference between these two things. It's more the intent, it's more where you wear them than them actually looking different, right? So the computer, when it was faced with all these examples we gave it in a hard problem of what's the difference between this lingerie and the bathing suit, it just punted in a way. It just said, I'm going to label pictures that are outdoors as bathing suits and pictures that are indoors as lingerie, right? So this is an example of, by letting it decide how to determine the difference between these pictures, it didn't do what we intended it to. There's no way for me to tell the computer, the job you have is to determine the difference between bathing suits and lingerie, right? It doesn't think about it that way. It says, I've got a huge stack of pictures that you tell me are one thing, and another huge stack of pictures you tell me are some other different thing, and I'm going to latch on to whatever I can find. I, as the computer, am going to latch on whatever I can find as the difference between these two things. And in this case, it latched onto outdoors versus indoors, okay? So you can imagine how this problem could crop up all over the place. And anyone that does machine learning for a living is going to say, well, yeah, duh, of course. If your training set is terrible, if your training set doesn't cover everything, it's not going to work well, right? But I want you to take two things away from this. One is building those training sets is really hard, especially for those of you that want to apply machine learning in a wartime or an intelligence gathering. You know, it's going to be really hard to find training sets that are useful. The other thing to take away from this is that you really have to pay attention to what it is you've actually taught the system to learn. And you have to double check that it's actually identifying what you want to, because it's really easy to fool yourself. When we first did this, we thought, great, this is working great. And I have other hilarious examples, or disturbing examples, really, like, you know, misidentification of legs as certain body parts. We actually had a racist version of this at one point, inadvertently. Like, it thought that people of color were more likely to be in nude images because our training set was skewed, right? And I feel bad about having a racist machine learning model, but it's really a problem of just we gave it the wrong data. We taught it the wrong thing, and it picked up on that. And it really comes back to, again, when it's learning these features, it's hard to know what's going on. So how does this connect to our planetarium and mosque problem? Well, this is something called adversarial examples. And basically what happens is, because these machine learning models are latching on to these tiny little details that sort of don't make sense to us as humans, it's possible to skew the inputs, the data, in ways that to the machine look hugely different. makes all the difference in the world that that pixel in the sky was different, but to a human makes no sense at all. And in this example, we have a panda. We add what looks like random noise, which results the other image, which to a human, it doesn't make any difference. It still looks like a panda. But suddenly, to the computer, it looks like a monkey, right? And I think it's really important to keep in mind, again, these are not systems that have any sort of intuitive knowledge about what they're looking at. It doesn't know anything about pandas. It doesn't know anything about monkeys. It only knows what it's learned from the examples we gave it. Okay, so sometimes this doesn't matter, right? Sometimes we're using machine learning algorithms to search for pictures of dogs in our Google Photos, which I have actually done, right? And it has no real-world consequences. Sometimes we're trying to use machine learning to recognize pedestrians and people on bikes for our autonomous vehicles, and it does matter, right? And what we're just now getting to the brink of is what happens when someone is intentionally trying to make it look like that person's not a person, or that stop sign's not a stop sign, or our military enemies are trying to intentionally skew the data that we're collecting to make our machine learning models see the wrong thing. And it matters, and it's going to be a problem. And we're at the beginning of an arms race with this, absolutely. And in some ways, it's actually already started. One example that you guys may not have thought of here is, of course, spam detection, right? So spam detection is an early example of where, when we first did this, people put really naive machine learning algorithms against this problem and had fantastic results. It was easy to determine the spam from the not spam in our email. But of course, the spammers intentionally tried to delude these algorithms, and it got to be a much, much, much harder problem. And you know how we ultimately got a handle on it? Yeah. We implemented systems called SPF and DKIM that lets us know where the email comes from with high confidence. So we abandoned, in a lot of ways, the pure machine learning approach because it wasn't working, because the adversaries here were able to fool the algorithms. Another high-profile one that just came out is Face ID. You know, if you guys saw the new iPhone, they did a lot about how they prevented people from spoofing that by having images or masks. But you notice what they also did? They put a special camera in that can sense depth using little IR dots, which that's what this is a picture of. So again, rather than just a pure machine learning approach, they added an extra verifiable data source here. And Windows Hello, which is their face recognition for login, does a different but similar kinds of things. So, you know, here are two sort of early examples of this arm race, and so far it's been hard to protect against them without resorting to something different than just pure machine learning. So that's that. So questions, I don't know what the time is. So, yeah, so a couple of minutes for questions, and then we can let Don speak.
Thanks. Any questions for Karl? So right in the middle here. There you go.
So what's the defense against trying to spoof or fool these algorithms, or is that still an area of research?
It's still an area of research. I think there's sort of two hopeful things. One is that people actually generate adversarial examples and then train the system to recognize them. And I think that's the success of that is dependent on your ability to anticipate what your enemy's going to do, right? And I think the other one is you can try to look at either the inputs or the outputs of the system to look for signs of tampering. So output would mean, hey, suddenly there's a lot more mosque being identified than planetarium, so maybe I need to go in and look at the data. But honestly, there's not great defenses against this at this point.
Thank you. Good question. Any others? All right. Well, I'm sure when we combine Karl's thoughts with Don's, we'll have more questions because they sort of play one into the other.
Hello, everybody. My name's Don, and a little bit of background about where I'm coming from is I'm building these systems as a career. I have a consulting company called Kasch. We're out of Maryland, about pretty small, about 25 people. We're very focused on building AI and machine learning systems for mostly commercial industry. And so, day in and day out, I'm building these things and not worrying about security. And then later on that night is like, yeah, you know what? That's going to be a problem one day, but not yet. So I think I'm really excited to talk about this because it's providing me an outlet to talk about what I'm worried about in the types of systems that we're building. And particularly in contrast to Karl's talk, I'm going to be talking about the idea of reverse engineering or gathering information from models that are deployed in the world. So more often these days, one of the reasons why you want to do machine learning is because you want to deploy this out into the real world and have it make autonomous decisions. So these systems can obviously be observed, and then, if somebody wants to do something bad, then they could. Right? So that's what my talk is about. So the first thing I wanted to do is talk about, in a little bit more depth, about how machine learning works in general, and so that I can explain how one of these systems could be reverse engineered. And I feel like it's pretty obvious, which is scary at the same time. So supervised machine learning, which is a portion of machine learning, but supervised machine learning is all about classification or regression, which means that we plug in some observations, we see this picture, or we see this information about an individual, we see the survey results, and we're going to predict some value, whether we're going to predict whether, who is this person? Is this a pedestrian? Is this a lemon? That's what supervised learning is about. It's about pulling one of these things. Is it going to rain today? What's the temperature going to be? So you can do all kinds of things with this kind of approach. It doesn't necessarily even need to be predicting anything about the future. When I say prediction, I mean I'm predicting something that is unknown. So it could be that I'm predicting a hidden feature of something. I could be predicting a value that could be observed but may be expensive to observe. So there's lots of connotations of prediction. So the way in general you can look at this is that a machine learning model or a problem out in the world, not necessarily a machine learning problem, you have observations, and I'm going to pass it into some sort of function here that is then going to return what the outcome is. So I'm going to pass a whole bunch of stuff about the image into a function that's going to return back whether it's a lemon or not. And so those observations is what Karl was talking about, were feature engineering, or with deep learning these days, less of that, and just giving it something raw. Most machine learning, supervised machine learning pipelines follow these three steps. The first is gathering training data. The second is then training a model. So I'm going to gather my data, and then I'm going to use a machine learning algorithm to train a model. And when I say model, think of it in a literal sense. So when I have a construction project, for example, and I build a model of that, the reason why you do that might not just be to have something fun to look at, but you want to see how it looks. You want to see how these things interlock. You want to say, what happens if this situation happens. So models are models in the sense that we're building a representation, an approximation of a situation, so that we can interact with that approximation and figure out what's going to happen without building the real thing and then interacting with it. And then we're going to use it. So once we have the model, then we're going to start interacting with it. All right. So this is the general step here. So so here's kind of similar to the spam detection. We use this a lot as a canonical example because it's one of the oldest ones that's been around in terms of detecting email messages that were problematic. And so a classification problem may be, given an email text, is this a scam or not a scam? And this is one of those, like, I've got a bunch of money and I need somebody in the U.S. to help me transfer it. And then we want to determine if it's a scam or not a scam. So there's a couple interesting things in this email in particular. And actually, I read an interesting paper about this later, but I'll give you some information about that. But if you look at this, there's things that are weird about it. There's like punctuation issues. Like the person seems to struggle to put spaces after their periods and commas. He starts it out with "dear friend," period. So this is a just generally odd email overall. And so, if we trained a scam detection thing, I could imagine that these are the types of features that the thing would look at. I read an article later that a lot of these scammers actually purposefully make these emails seem scammy so that they filter out the people that can detect scams easily. So, my grandmother, for example, can't tell the difference between scams, and she's the one that falls for it. Meanwhile, the person that's middle of the road that would figure out that it's a scam later, they won't waste their time. So that's kind of an interesting exploit. But anyways, this is a text example of scam detection. And then facial recognition is one, computer vision one that is obviously happening a lot. And I want to pass an image to the thing, a new image that I've never seen before of an individual, and say, who is this? Is it somebody I know? Is it somebody I don't know? Is it this person or is it not this person? Is this person wearing a military uniform? Is this person tall or short? Right? So there's all kinds of things I could be doing with computer vision in people. And these people are in different scenarios and different situations, right? So the way I would handle this from a classification standpoint is I could ask this, is this Don Miner or not? That's how I would frame a machine learning problem to do facial recognition. So to go through the 3 steps I had originally, the first thing we're going to do is we're going to gather training data, which is, like Karl mentioned, is actually the most important thing. And to kind of echo one of the questions that he answered, I think gathering training data is probably one of the most important things to be secure. Because where machine learning algorithms fail spectacularly is on the edge cases that we have not provided it training data to really understand. So the classic example that I heard of from several times was there was some like DARPA thing. I don't know if it was DARPA. I shouldn't throw them under the bus, I guess. But they wanted to detect like in an image whether there was a tank or not. And they put the tank behind the bush. They put it in front of the bush. They put it to the left of the bush, to the right of the bush. And they gathered this training data, and they were outside all day taking pictures of these things. And at the end of the day, what happened was that the machine learning algorithm determined that if it was night, then there was no tank, and if there was day, there was a tank, because they started taking the tankless pictures at night, right? So when you want to be able to detect tanks during the day and night, you need to have examples of you need to explain the boundaries to something. When I explain something to my child or my children, I say, hey, this is a picture of this, and this is not this. And this is this in this context, and this is this in this context, right? So these machine learning algorithms will super hyper-focus on these things, and on these boundaries are where the problems happen, or scenarios that we haven't seen before. Like one of the examples that we looked at closely was the most recent Tesla crash in California. Observed a scenario that wasn't really accounted for, and it basically decided to throw the car into a bulkhead, right? So the Tesla will drive great in a clear road on types of things it's been trained on, but there are certain scenarios that it hasn't been trained to see yet. So gathering training data is important. We're going to observe the environment, and then we're going to say this is what happened. So I'm going to observe this picture and say, this is Ricky. Okay? All right. So to train a model, I have all that training data, and how much training data I have depends on how much I want to be doing with it. I'm going to use a machine learning algorithm to create a model. So the output of the machine learning algorithm is an object of some sort, a piece of computer code that trains it, and I can serialize it out as a file and distribute that. And so I create this model, basically, from this training data. And the goal of the model is to maximize accuracy in the training data, meaning that I get 99% of faces correct, or I get lemon, lime 100% correct. That's our goal with this model. So that when we pass it a new image, we continue to be accurate. So then I use the model so I can pass a new image of somebody that I've never seen before, and then it's going to predict who that person is without me asking who that person is. So maybe before in the training data I said, okay, this is the picture and this is who it is. This is the picture and this is who it is. Here in this case, we pass the picture and then the machine learning model responds back and says who it is. It says it's Ricky. So this model is a thing, and it's actually quite common in our engagements when we're building AI systems to wrap these models in some sort of like internet-based service that can be accessed by maybe third parties, Maybe it's plugged into a website of some sort. You know, it's making decisions out in the real world, maybe on the internet, maybe in a robot, something like that. And from an outside observer's perspective, I don't really necessarily know how it works. I don't know which machine learning algorithm it used. But I know how to give it input and I know how to give it output. So I can treat it as like a black box, right? So one of the attacks that I want to talk about, I'm going to talk about two attacks here. The first attack is a reverse engineering attack where we can actually, it's been shown that we can fiddle with these models and actually get a model of the model to determine what we think that model might do in different scenarios. And then we can let our imaginations go wild about what we can do with that. So let me explain how I do that first, and then we can talk about what we can do with that. So the first thing that we're going to do is we're going to create some made-up observations. Maybe these are real observations, or they're made up, or adversarial observations that we are plugging in to see how it would act in a certain scenario. So like, for example, if we had I'm going to be kind of grim here, but let's say that we have like a turret out in a field that automatically detects objects walking by, and if it's the wrong type of object, I'm going to light it up. Okay? So I could, if I created a model, I could determine, you know, is it going to kill deer? Is it going to kill rabbits? Like what is it? And you can, I'm using this grim example because, you know, if I'm detecting whether or not something's a hot dog or not, that's one thing. But if I'm detecting, you know, objects like vehicles in the wild that can actually harm people, this is really important. So by fiddling with these models, we can start to determine on which boundaries certain types of things lie. And I may find gaps in the model's understanding, exploitable gaps. So what we do now is we take this adversarial data set, which is where we plugged in all these random observations or targeted observations, and we have a new training set. I'm going to use a machine learning algorithm again to train on mimicking the original machine learning model that we do not have the internals for. So what this means now is that I now have a reverse engineered model that can behave and act like the other model that I may not have access to. And we can pass it things and see what it says. So we basically use machine learning to basically mimic something else that was done. So, you know, we trained the machine learning model and then we basically were able to mimic this intelligent agent. So this is an example of some research. I won't go into the details, but this is just one example of a paper where they reverse engineered a pretty complicated ensemble base, which means that they have multiple neural networks that are voting to determine the outcome of a scenario. And they mimicked an ensemble with a single model, which means that it wasn't even the same architecture, it wasn't even the same approach. And while the ensemble method was getting 61% accuracy, the distilled single one was getting 60.8. So basically, they were performing almost identically. Okay. So what are some use cases of reverse engineering a model? So the first one is, you know, if I'm interacting with a model, obviously if I have an open model to the internet and I don't have any rate limiting or anything like that, and people can go hog wild and contact this thing as much as they want, you know, that's a problem in itself. So if we instead create a model of the model that we're attacking, we can then attack the model of the model and determine the weaknesses without maybe alerting our foes. So, I mean, when I was coming up with this example and we were using the facial recognition problem, imagine that you were trying to fool a facial recognition camera to let you into some building, right? And you kept walking up with it with like a printout of my face, right? You walk up to the thing and it's like, did it unlock the door? No. Okay. I go back, print out another one, I come back. I mean, eventually some security guard is going to see you like putting paper up against this thing, right? So if you can figure out how to reverse engineer it, then you can interact with that model instead of maybe giving off your cover or something like that. Email scams and email spam is a good example of this where you can just generate tons of emails and start seeing, this is why machine learning stopped working over time, was because you can just generate emails to see if they get caught by the spam filter or not. And if they don't get caught, that means we tickled it in a way. And also, too, these spam filters are commercially available. So the spammer can buy the model and then see which ones are going to pass the spam filter before they send it out. Okay. On facial recognition, you can just keep trying different things and see which ones pass through, and basically regenerate the model of the facial recognition system that you built. The other thing, too, is that if this machine learning system is then interacting with and making decisions out in the real world, you can start modeling what this system may do. So one particularly scary use case that I can see about predicting what an autonomous system may do is in automatic stock trading. And I think there's been a couple of books that have been written about the world's collapse due to this problem. But basically, we actually built one of these things. I was working for a hedge fund, and we wrote a text model that was reading certain text documents about companies. And we figured out that based on some features that were being automatically detected through the deep learning stuff they were doing, that we were able to determine whether a company was about to take a nosedive. And it wasn't a huge predictor. I mean, in finance, all you need is like a couple basis points to make something worthwhile. But we saw a slight correlation between our model being able to predict the company being able to take a nosedive based on some tech stuff. And so what we did was we ended up taking the company we were working for's financial documents and plugging them into our model and seeing if we were showing the same predictors for this bad thing to happen, right? And we found that since we knew how the model worked, we were actually able to tweak the language to get a higher score on our own model. So we were able to tweak our language by removing some words and replacing them with others so that we would have a lower nosedive score. So when you start talking about knowing that there's agents on the stock market or self-driving cars or military apparatus or whatever, internet agents, bots, if you can predict their actions, you can tickle them in ways to get them to behave in the way that you want. You can almost take control. And so having a reverse engineer model can really help with that goal. All right, I think there's all kinds of other fun things you could do with a reverse engineer model, but this is something that we need to be starting to worry about. The next one is more of a privacy concern, is the second attack that I wanted to talk about, which is inverting models. So what I mean by an inversion of a model is I have a training data set which may be comprised of private information or classified information perhaps, or information that I do not want to necessarily have individually released. And I'm going to create a model from that data, and let's say that's facial recognition. I'm going to use that as an example. And the way this model works is it's going to have a few names out of there, and I'm going to plug in a picture, and it's going to return back with a confidence score, how strongly I feel who that is. Okay, and I'm just going to say, okay, well, it feels like this picture is me, and it got it correct. Okay, so that's what this thing is doing. But let's say that this is a scenario where it's like a secure situation, perhaps, or I don't necessarily want my personal identity revealed just because I'm in this model, right? So what I'm going to do is I'm going to pass in a bunch of random photos never seen before of different people. It has to be people, though, because that's what the network understands is people. If I pass in broccoli, it's just going to be confused. But I know at least that it's people, and so I'm going to plug in this picture of Danny DeVito, and it's going to return back like I said Danny DeVito looks most like my business partner, and then I'm second, and Karl is very low on the Danny DeVito scale. And so what happens is as I pass these different images and I get these different confidence scores, I can layer them together and start getting a picture of what Don might look like. So if I pass in a picture of Danny DeVito and I'm only 33% Danny DeVito, but I don't know, I look like a bunch of other bald people with beards. All right, so this was a paper that was released a couple years ago, and what they built was an inversion attack in the exact same thing I was talking about. And this picture on the left was reconstructed from a black box model to show what kind of face would trigger this person's name. So we did not have access to the training data. The researchers didn't have access to the training data. They did this attack that I mentioned, which is what I based my slides off of this paper, where they submitted these pictures to these individuals and were able to recompose an image of what they thought this individual looked like just by knowing their name and having access to the neural network that has created it. Okay. So, I mean, in this case, I mean, it put a smile on the guy, I guess. That's nice. You know, in this case, it's not that big of a deal, but it's something that we need to be careful of when we're talking about being able to reconstruct these models. So some of the use cases of this is, you know, I kind of mentioned a couple, but extracting original. The other thing I want to mention too is that when you have training data, there are also patterns too when you resubmit a piece of training data where it will feel really strongly about that single piece of training data. So if I submitted a picture of me that said Don, and then all of a sudden I submit the exact same picture later on, it'll have a very strong feeling that that's me because I match up exactly to a picture in its data set. So you can also too kind of like probe it and see what pictures is actually it's been trained on. So you know, some people have shown that you can extract original segments of text. You're not going to be able to reconstruct like entire email blocks, but you could extract segments of text. You could extract certain features like survey results. So one of these papers was able to determine if you cheated on your wife or not based on your survey results. I'm not quite sure what that means, but I didn't read too far into that one. The reconstruction of images is another one. And then anything that's like protected and private, you know, that may be in that training set are things that could be exposed to this problem. So I think I shared my presentation with my colleagues, my other machine learning colleagues, and I generally agree with them too, that these I feel are like pretty obvious results. Okay, so we can reverse machine learning algorithms. So what? We can invert them and pull out some training data. A lot of times this is not possible. You know, it's naturally secure because, you know, reverse engineering a model, like so what, it's not that big of a deal, or your adversaries don't have direct access to this model necessarily, or the sensitive information that could be extracted, you know, is set up in a way that it's really actually quite hard to extract. There's a number of reasons why this just isn't going to be a problem. What makes me nervous is that we are building these systems without even thinking about this, right? Nobody's sitting down and thinking like, hey, what could an adversary do here? Like, what would the outcomes be? Like, that conversation never happens. You know, we deployed this model to this financial institution that's looking at text documents to determine, you know, whether or not a company's going to take a nosedive or not. I mean, we kind of toyed with the idea, but we didn't believe that an adversary would actually be able to figure out that we could do this, right? Well, there was this kind of like security through obscurity situation where nobody knows that we're doing this to begin with, so what's the big deal? But then you start dealing with like social factors and people doing like espionage, figure out like what models you have running, and it's not that far off before we start figuring things out, right? So so for example, and some of these things could be really solved very simply. So the solution that the facial recognition reconstruction people did was that what they said was the solution to this problem where I'm passing back the probabilities of, or not the probabilities, but the scores for the individual people of this image that I have here on the right. That if instead you just mask that and you only return back the one name of the person that has the highest score, or even just the score for the person with the highest score, and you do not return the other scores, that basically makes this almost impossible to reverse engineer or to invert. But that's like a thing to think about. Like, to me, it's nice to have those other numbers so I can kind of see like where it's getting confused. But from a security perspective, I might want to mask that. So I guess like my answer to, I think the first step in securing these models and when we're building autonomous agents that are doing things that are important and can have bad consequences of things, what's the worst thing that can happen, we need to at least be thinking about the adversary, right? I don't think these things are going to be super hard to secure in that sense. I think the problem that Karl suggested actually is kind of different from these two, where that is, I think, a serious problem with the training set. But the problems that I'm describing, the inverting and the reverse engineering, is more just how do we protect against it? And I think there's a pretty obvious solution. It's just going to be different for every case. But I really am trying to drive home the fact that let's at least think about it. talk about it after we build a system. What can an adversary do? All right. That's all I got.
All right, thank you. So you heard some interesting information around security and reverse engineering around machine learning and what we can expect from it, what we can not expect. Are there questions? We're here, sir.
Karl, I guess I'll go back to you because I was working a little bit up with the DoD and the Project Maven piece, but to kind of roll that one back the way that you're talking about it. My background is I spent life as an imagery interpreter, and so we used to learn to recognize camouflages and deception and things along those lines. But if your training bias is introduced as we're trying to train these machines to recognize vehicles, buildings, things along those from full motion video, it sounds like it's relatively easy then to, after that training set is done with a very simple set of camouflage that a human would pick up automatically, a machine might not, if you could just change the equivalent of 1 or 2 pixels in the actual image. And I just wanted to get your thoughts on how effective something like a Project Maven really is, given the vulnerabilities that you guys have pointed out today.
Just to be clear about these adversarial examples, they are a little harder to exploit than what you're thinking, because it's not like the same image always works. So what they do when they generate these is they send thousands or hundreds of thousands of images through the system until it finds one that confuses it. So it's much harder in the real world. So your example of like, if we take our digital camo and we put a really bright spot on it and it's the equivalent of that pixel, it's going to be harder than that. But I do think it's going to potentially be possible to sort of systematically introduce bias. And I think the spectacular failures that I was showing for those single pixel attacks, I think those are probably going to be easier to deal with. It's the bias that's going to be harder, right? It's more boiling frogs than spectacular failures. It's going to be the really hard things.
Thank you. Other questions? Back here in the back.
Hi there, Major Church, Canadian Army. I know we're talking about learning here, machine learning. My question is, where do we go from here in terms of other areas of artificial intelligence, such as reasoning or perception or abstraction?
So I guess let me start by answering your question about how we got here, maybe in the past few years with machine learning. I did my PhD in machine learning about 10 years ago now, and it wasn't as hot then as it was now. And so in terms of some perspective on why we got here, I think has a lot to do with computing power. It has a lot to do with like large-scale data systems that have allowed us to collect this data. It has a lot to do with sensors that are collecting lots of data and things like that. There have been some advancements in machine learning, but for the most of it, I think I attribute it to these underlying data collection systems. And so what happens is that an organization is sitting around and they want to collect lots of data, and they do collect that data, and then they do the obvious things with it first. So that's where business intelligence comes in. So I want to summarize my data. I want to answer basic questions about my data. Okay. So you do business intelligence, then you get kind of bored, and you say, well, what more can I do with my data? What more can I infer? Right? And that's where machine learning comes in. Machine learning is the next step. So business intelligence is about figuring out what happened in the past. Tell me what's happened. How did my sales do? How was this campaign? How did this work, right? And without business intelligence, that's actually quite hard to do. And a lot of businesses were running blind for a long time. Machine learning is about predicting things that may happen in the future or may be unobservable, right? If we build this thing, what is it going to do? Or can we build these vision systems that determine that this is a lemon or not, right? So we call that also predictive analytics is one term that we use. So one thing that I see that we're moving towards right now, is towards what we call prescriptive analytics. So not only is it determining what it is going to do, but what I should do, and then do it. So this is where we start transitioning into building predictive models to make predictions about the future, and actually having these agents impact change in the world that they live in. And this is an interesting problem because you have to bridge a couple gaps here. The first gap is a feedback loop in the sense where you have to have this system continue to learn because it knows that, you know, if I act in this way in this environment, this is what I predict is going to happen. But then that may change the environment itself. So predictive analytics and basic machine learning are observing and making observations about the scenario. When you start interacting with the environment, it completely changes everything. So this is where we start getting into autonomous vehicles, I think is the most tangible one for us to wrap our heads around, where the car is not only seeing what it's seeing and predicting what would happen if I did different scenarios, but then actually adjusting course in this, right? And then we're also seeing autonomous systems built in like cybersecurity, for example, to identify like threats as they're happening and then taking action on that instead of just alerting somebody that it's happening. And this is, so I think that's where it's going. That's my opinion, is that we're moving from predictive machine learning into prescriptive autonomous stuff, and that's super exciting and super scary at the same time.
Actually, I have one quick example that goes with that. So one of the problems they had early on with the autonomous vehicles is they had to understand what happens at a four-way stop, right? Like who should go first, and you know, and sometimes the autonomous vehicle needs to be the one that goes first, right? So there's these certain kind of bikes you may be familiar with. They're called fixed gear bikes, and so unlike a normal bike where the pedals go backwards and it's just free wheels, with these it's a direct chain connected to the wheel. And what it allows people to do is you know how a unicyclist can stand still on a unicycle? The fixed gear bike people do that on these fixed gear bikes, okay? So what was happening is these autonomous vehicles would show up at an intersection and they'd see someone on a bike with both of their feet on the pedal, which the car thought was a biker about to go somewhere. But because it was these fixed gear bikes, they were actually just sitting still and waiting. And what would happen was the autonomous vehicle wouldn't go first, which is what the biker would expect to happen. And you would end up in the situation where no one went anywhere, right? So I think it's a funny example in some cases, and it's definitely what Don's talking about, how these systems interacting with the world is changing the world. But I think the bigger thing that sort of pulls on is that the problem was the autonomous vehicle didn't know this was possible. And to kind of go from what I was saying before, it doesn't have any common sense or context about the world to actually reason about things that it doesn't know about already, right? And I think that for true intelligence to happen, we're going to have to start to have some of that. But as Don was saying, we're not actually making progress really in that field. We're really taking old approaches, throwing huge data sets at them with lots of computing power, and it's like magic. It works better, but we're not making those sort of fundamental advances towards real intelligence.
Quick question on cybersecurity of these. Who's taking care of the cybersecurity of these algorithms? I understand how the IT is working and sort of how the OT is working, but who's actually looking at the cybersecurity of the algorithm, especially as it's deployed?
So your question is, who's talking about the security issues that maybe we're talking about? And
yeah, I mean, if I'm worried about the the firewall, I'm worried about the an insider threat, and I'm worried about the whatever. Where does this kind of fit into the hierarchy of what the CISO or whatever is worried about, the extent to which his machine learning may be telling him the wrong lessons?
Yeah, well, I think I think my answer is similar to what I would recommend with general security practice, in the sense that the CISO is obviously responsible for security at the organization, but security is about not just the CISO, but also to instilling a sense of security in all the people that are working for the organization, and that they're operating in some sort of secure manner, right? That's a very idealistic thing, right? But I guess what I'm saying is that it's a full organization responsibility between the CISO making sure that there's policies that are involved that are protecting the organization, and that also too the machine learning engineers are that have just been plucked straight out of a PhD program are taking these things into consideration as well. So as of right now, who's looking at this? Nobody. I think I've never had a security person at any of the companies I've worked at review our stuff and determine whether or not these were posing any sort of threat or not.
Thanks very much, Don, Karl. Appreciate your time and your preparation.